first I'm going to find I'll find the cross product, the B cross C. So, whoops. So I like to set up the cross products kind of like the determinant. So I'll do so B was given by 2 minus 2, 0, and C was 1, 0, 3. And then, so I'm going to find it like the determinant. So I sort of take away the first column, and I'm going to go minus 2 times 3 minus 0 times 0. So that's going to be, I might just actually write it straight away. So yeah, so minus 2 times 3 minus 0 is minus 6 I, and then excluding the second column, so we have minus 2 times 3, which is 6, minus 0. So again, we get minus 6j. And then the last one, we exclude the last column, and so it's plus 2 times 0, so that's 0, minus 1 times 2, so it's plus 2k. So we've found B cross C, so now we can find the scalar triple product, which is A dot B cross C. And so A, so that's it. A is at minus 4, 1, 5, so it's minus 4I plus J plus 5k and we dot that with the B cross C that we've just found. So that's minus 6I minus 6j plus 2k. So that's minus 4 by, so that's 24. And then plus 1 by minus 6 is minus 6. And then 5 by 2 is plus 10. So that gives us 28. And so the geometric interpretation of this is going to be, it's essentially, it's if the vectors A, B, and C, if we take them and form a 3D shape from them, we've found the volume. I've got a picture to show you, but I'll just write it first. So I'll tell you what. Typing this might be easier. I'm not sure I'm going to pronounce this right, but I think it's a paralipid. So I tried to draw a picture here. So if we've got B cross C here, then just the magnitude of that is equal to the area of this here. Direction is actually perpendicular. You take the dot product and you're sort of projecting A onto this direction here. You get like the height of the shape, and so you've got the base here times the height, and then that's why the scalar triple product sort of geometrically is the volume of that shape. Does that make sense to everyone? And if you look at the formulas here, you can kind of see that. And then if you think about how to find the volume of such a shape, if you knew the side lengths and the angles between them. Okay, I'm going to move on. No one has any questions.
Do we have to draw one of those for each? Like little triple product?
No, I kind of I drew that sort of so that you can sort of see it geometrically. I guess when I was thinking about the problem, I was thinking, well, how can I, like, how does this make sense to me? Like, if you look at the formulas, like, you can see that it is the volume of but I don't think that picture is necessary in your answer if you want to draw a picture. Like, if it helps you sort of understand where the geometric interpretation is coming from. I guess I just want you to kind of make sure that I'm telling you that I guess that it's the geometric interpretation. I hope that you would sort of consider the shape and make sure that makes sense for you as well. Like, you can see why that is the geometric interpretation.
Can you quickly review the question 1, part 1?
Sorry, what was that?
Can you just quickly review the question 1, part 1?
Yes.
Yeah.
Which part of it?
Do the recording of the part 1.
This one?
Yeah, that's cool.
Did you have a... Yeah, cool. I assume you just took
Thank you. Yeah.
Photo. No. Okay, we'll move on to... Oh, wait. Okay, the triple product. So we've already found B cross C. So to find A cross B cross C, we just have to, instead of finding the dot product with B cross C, we're going to do a cross product again. So there's A, and we're crossing that with what we found for B cross C. And again, I like to sort of do it as a determinant. So it's 1 times 2 is 2 minus 30. So it's 32i. And then it's going to be minus 4 times 2, which is minus 8, minus 30. So that's minus 22j. And then it's going to be plus minus 4 times minus 6, so that's 24, minus 6, so that's plus 6, so it's, plus 30k. So that's the vector triple product there. Okay, I'm going to move on to question 2 now, unless anyone has any questions. Okay, so we've got a position vector here, A, given by minus 2i plus 3j minus 2k. And so that's currently in, I guess, in Cartesian coordinates. We can sort of see very simply by inspection that x is minus 2, y is 3, and z is equal to minus 2 in Cartesian coordinates. But now we're going to compute the position in cylindrical coordinates. So we've got, so in cylindrical coordinates, we have the radius of the cylinder given by rho, and that's just equal to the square root of x squared plus y squared. So that is equal to minus 2 squared plus 3 squared, the square root. And so that's 4 plus 9 is 13. So the square root of 13 is the radius. And then the angle given by phi. And so, I mean, I think these formulas should be in your lecture notes. So that's given by arctan of y on x. So that's arctan of 3 on minus 2. And now when I put that into my calculator, I got minus 0.983 radians. And make sure that you're in radians. We don't want degrees. But if we think about sort of the position of the position vector, so we're actually in, so we're minus 2 plus 3j minus, so we're coming down something like that is A. Does that make sense to everyone? And so when you think about, whereas like your angle phi here, if we're coming off the x-axis, then it should be phi needs to be greater than pi on 2, because we're in this quadrant here, kind of, but less than pi, because we haven't like swung around into, so we're here. We haven't swung into here, but we've passed the y-axis here. So minus 0.983 radians is not quite right. So, but since x is less than 0 and y is greater than 0, we've got to add pi to that answer, basically. So therefore phi is going to equal to 2.1588 radians. So if you just think about where your position actually is, you should be able to sort of figure out like a range that you're expecting your angle to be in, and then you'll be able to work out exactly what it should be. So therefore, the terminal point is at, so we had rho, phi, and so I didn't have to find z because in Cartesian and cylindrical coordinates, the z is the same. So we found it to be root 13 was rho, phi was 2.1, I'll just do 16. I'll just see if I can do it over here. So we had root 13, 2.16, and then z was the same, so that was given by -2. And so that's in cylindrical coordinates. Did anyone have any questions about that one? Cool. So we're going to go on.
Can you just explain the why theta is not equal to the minus 0.983?
So minus 0.83 radians. So because tan is the periodic function, you know, like, so the answer to this has multiple solutions, but we know the position vector, because we're at x is -2, y is 3, and z is k, it means that we're in this quadrant. And so so here along the x-axis, phi is equal to 0. And then we go around with increasing phi. And so along the y-axis, phi is equal to pi on 2.
Oh, and
so we know that we're in this quadrant for A. So we know that our radians should be between pi on 2. So that's like 1.57 and pi. So 3.14.
So it's just pi minus 0.9. So we got 2.1. That's right.
Yeah. So I just added pi.
Cool. Yeah.
Yep. So now I'm going to compute it again, but this time I'm going to do spherical coordinates. So this time, so in spherical coordinates, the radius is given by the square root of x squared plus y squared plus z squared. And so that's going to be, So 2 squared is 4, plus 3 squared is 9, plus minus 2 squared again is 4. And so that's going to be root 17. And then to find the angle, so we've got theta this time, so we have arc cos is z on r. So that's going to be, so z is minus 2. And r we just found was root 17. And so this time when I put that in my calculator, I get 2.077 radians. And so, again, I guess I think about where, like, what the angle theta should be. So in spherical coordinates, phi is going to be the same. But if I go back to that little diagram that I chose, so our vector A is sort of, because z is negative, it's pointing down this way. So when I look at the angle theta, so that comes down from the z-axis. So that's that angle there. So we're expecting it to be bigger than pi on 2 this time. But when I put it, I just used a calculator, arc cos minus 2 on root 17, I got 2.077 radians. But when I thought about it, that's bigger than pi on 2 as expected. So I don't have to make any adjustment to that. And phi, as I mentioned before, is unchanged from the cylindrical value. So, therefore, the terminal point of this position vector is at, so r theta phi, we had r was root 17. Theta was 2.077 and phi was 2.16. So did anyone have any questions about that one? I think the important thing to note there is that just think about where your position vector actually is in 3D space, and then you can sort of check that the angles that you're calculating are correct. Because, of course, like, cosine, tan, sine, they're all periodic functions. Okay.
So does theta go from the z-axis down to the y-axis in that diagram?
Yeah, I'll try it. Maybe I'll draw that again because it was getting a bit. So theta, hopefully I haven't mixed up theta and phi from your lecture notes. because you will find sometimes that they're defined differently. But so my position vector A, I think it was -2 this way, 3 this way, and so it's pointing down here. So the z-axis is theta is equal to 0. If you're along the y-axis, that would be theta is equal to pi on 2.
Oh, okay, cool.
And so you know that you're bigger than pi on 2, but you're before you get to theta is equal to pi when you're pointing sort of down the x-axis.
Yeah, I just got my coordinates mixed up, but I get it
Yeah,
now.
no worries. Okay. So I want to rewrite these surfaces in cylindrical and spherical coordinates. I have 3 prepared, but I don't know if I'm going to get. We'll see how we go for time. I'm not sure if I'm going to get all the surfaces done and also look at question 4. So for this one, so we've got this surface, it's x squared plus y squared plus z squared equals 4. So I recognize that that's a sphere, but y is greater than 0. So we don't have all the negative values for y. So that kind of, it's half a sphere. So in cylindrical coordinates, we have x equals rho cos phi, and y is equal to rho sine phi. So that's just, I guess, formulas that relate the Cartesian coordinates and cylindrical coordinates. But if we take that, then we can see that when we take, the formula that represents the surface, then we have x squared plus y squared plus z squared is equal to 4. Sorry. What I wanted to say before that was, sorry. So if x is rho cosine phi and y is rho sine phi, then that implies that x squared plus y squared is equal to rho squared. And so then when I have this surface that I've got in Cartesian coordinates, then I can replace this x squared plus y squared that I've seen here. And then we just get rho squared plus z squared is equal to 4. And obviously in cylindrical coordinates, we still have z as is the same as in Cartesian coordinates, so we don't have to do anything to z. And because y is greater than 0, then that means that rho sine phi is bigger than 0. And because we've got rho is, I guess, always positive, so that means for this to be positive, sine phi has to be greater than 0. And when does that happen? That happens when phi is between 0 and pi. Now we can represent that surface in cylindrical coordinates, and so therefore rho plus z squared is equal to 4, and phi between 0 and pi, that represents the surface in cylindrical.
I just got a quick question. With the
Yep.
domain or whatever, the 0 to pi, do we include pi or like exclude it?
I included it because
Like, is that going over 2 points? Is that mapping 2 points or what? If you know what I mean.
no, it's not. It's not. It's because this is not. Hang on. I think if I draw it, so it's for y greater than 0. So it would be like a sphere sort of that way. So phi going from 0 to pi, say around the middle, would be going like that.
Oh, yeah.
And so, we haven't, it would match up if you went all the way around and you got to 2 pi.
Yeah.
But we're not, in my case, the surface that I'm looking at is only for y greater than 0.
Yeah.
So that's why I did all the way from 0 to pi. Okay. And now in spherical coordinates, so, using the formulas that relate Cartesian to spherical, we get that x is r sine theta cos phi, y is r sine theta sine phi, and z is equal to r cos theta. And from that, if you take x squared plus y squared plus z squared, and if you sub in all of those and play around with it a bit, you get that equals r squared. So therefore, to write it in cylindrical coordinates, it's pretty easy. We just have, so x squared plus y squared plus z squared is equal to 4. Then we just get r squared is equal to 4. Or r just is equal to 2. And we can ignore the r equals minus 2 here. Like, we don't have to, when we take the square root of both sides, we don't have to consider the minus 2 because we're in spherical coordinates, and as part of that, r is always greater than 0. Because otherwise you'd sort of be doubly defining things. We use the angle to go, I guess, the other way. And so phi carries over the same as before. And there's no restrictions on z. So so we don't have to consider like what theta has to be. It just theta just goes from 0 to pi as it does in spherical. Coordinates. So r equals 2, theta is from 0 to pi, and phi is also from 0 to pi. And so that's the surface in cylindrical and spherical coordinates. I'm going to skip the next one I'd planned, and I'm going to look at rewriting the surface x equals 4. But I mean, you just want to do similar things. So x equals 4. So in cylindrical coordinates, x is equal to rho cosine phi. So therefore we have rho cosine phi is equal to 4. So this is an implicit definition, but it states the relationship between rho and phi. So I might just type this actually. So it's the relationship between rho and phi, and the minimum value of phi occurs at rho occurs at phi is equal to 0. So, I mean, if you're looking at this as a picture, so, x equals 4 is just the plane, it crosses the x-axis. It's parallel to the ZY plane. And it's at x equals 4. And in cylindrical coordinates, so r is coming out and phi is coming out this way, if that makes sense. So, this is the length of this is my r, and how to represent this point on the plane, the length of that is my my rho, and then the angle here I've put this is the x axis, and so that's my angle phi in between there. And so here I've sort of done so rho is going to be between 4 and infinity, because as the angle increases to reach the plane, I have to take a longer radius here, and the phi is between minus pi on 2 and pi on 2. Or if I just consider that in 2D, it might be easier to sort of see. But if this is x and say that's y, then you've got this is x is equal to 4, and so that's the length rho, and then this is the phi, and as as phi increases, the rho has to increase, and then so that's a relationship between phi and rho to represent that plane. And then in spherical coordinates, we get so x is equal to r sine theta cos phi, and so again we get an implicit formula, so that r sine theta cos phi is equal to 4. And so this time the minimum value of r occurs when sine theta and cos phi are at maximum. And so we get again that r is coming from 4, and it's between 4 and infinity. Theta is between 0 and pi, and phi is between minus pi on 2 and pi on 2. And so we don't include the endpoints here because sine, so the endpoints would give sine theta is equal to 0 or cosine phi is equal to 0, and if they were both equal to 0, then we'd have 0 equals 4, which is not true. So that's why we haven't included the endpoints there. Okay. I'm going to look at question 4 now, but I'm probably not going to get all the way through it. But I think there's also some pointers on the recorded tutorial as well for this question. So we're going to consider the space curve formed by the intersection of the sphere r equals 2 and also the cylinder given by x minus 1 all squared plus y squared equals 1. And so there's a space curve that you can see on your assignment that has the intersection between them, and that's given by this parametrization here. So we're going to confirm the parametrization given here satisfies that line of intersection. So in Cartesian coordinates, the sphere is given by x squared plus y squared plus z squared is equal to 4. So that's equation 1 because, so it's because it's r, so the radius is given by 2, but it's is equal to r squared, so that's 4. And the cylinder is given by, as above, I guess. So we'll call that equation 2. So we can rewrite that as y squared is equal to 1 minus x minus 1 all squared. So if we substitute equation 3 here into 1, we have, so we get x squared plus y squared, but we're going to use equation 3 for y squared here. So it's 1 minus x minus 1 all squared plus z squared is equal to 4. And so if we expand and simplify the left-hand side, we get x squared minus x squared, so no x squared, and then we get minus 2x, so we get 2x. The ones will cancel, and then we're also left with this z squared. So that's if you sort of expand this and simplify. And if we substitute the parameterized forms of that space, the space curve we had, so you know, the ZTs and the XTs, we get 2, 1 plus cosine t plus, so it will be 2 squared is 4 sine squared t on 2. So we want to use the double angle formula, so we're going to rewrite it like this. Oh, that should be a plus. And we can rewrite 1 as sine squared t on 2 plus cosine squared t on 2, because we know that, sine squared x plus cosine squared x is equal to 1. And here I've used the double angle formula to rewrite that cosine 2t on t as cosine squared t on 2 minus sine squared t on 2. And then we've still got the plus 2 sine squared t on 2. And if you if you just simplify this, you eventually get to 4, which is the right-hand side. So that means, we've shown that the xt and the z of t satisfy that line of intersection. And then for y, we go back to that equation 3. We have y squared is equal to 2x minus x squared. Is that what I have? Yeah, so that was sort of expanding 1 minus x minus 1 squared, all squared. And then again, we want to sort of test that parameterization. So I look at yt squared is equal to 2xt minus xt all squared. So the left-hand side is just yt all squared is equal to sine squared t. And the right-hand side we have is equal to 1 plus cosine t minus 1 plus cosine t squared. And so if you expand that, you'll get to sine squared t. I'm not going to do it here because we're running out of time. And so that's the same as the left-hand side. And so thus, the parameterization for x t, y of t, and z of t satisfy. Because it's essentially, you know, that line of intersection, that needs to lie on the sphere and it needs to lie on the cylinder. So I've run out of time to go on, but I mean, sure. That's not quite all of it, but maybe I can show it in 2 parts. If you have you taken a photo of that, and I can scroll down, and you can take a photo of the bottom. But yeah, I mean, the next parts of the question are, you know, if you define the parametric, you know, as x of t I plus y of t j plus z of t k, and then you just need to differentiate, you know, all the different parts to find the velocity vector and then the acceleration vector. And that's it. If you have, I guess, feedback for me about how I could run these tutes better, like, you know, this is the first time I've done this. I'm sure we'll get better at it, and, you know, I hope that I've done okay. Where would you like to go back to? Oh, back up on this page. Is that good? But yeah, feel free to give me feedback, and we'll yeah, and I'll try to take that on board for the next ones. So, thank you, and yeah, goodbye.